Dear Amy, it is the 17th of June, and I'm just in my lab trying to run experiments, trying to make some progress. And I thought I'd just kind of I don't know, make a video. I have a whole bunch of video intros, so this might become part of it, but I don't know, maybe we'll get something out for you to see about what I'm doing. So this is over here, it's where I'm working. This bucket right here, this is our artificial lake. If you look in here, it's just sand. It's actually playground sand. At the bottom, it's about, I don't know, 2 inches of water. Then we have this PVC tube, which is the basis of our seepage meter, is that we can isolate this area from the rest of the lake, and we can measure seepage in there and then extrapolate from there what's going on with the rest of the lake. Usually we have this stuck inside here. This is called a magnetostrictive sensor. It's little sensors on the inside of this brass fitting, and there's a float with a magnet in it. Where is it? There it is. So when that goes up and down, it gives out a different reading. And this thing is supposedly accurate up to 30 microns. So in theory, that thing should be able to detect a change in water level at 30 microns. That's 10 to the negative 6 meters. So what's that, like 1,000 times 3 thousandths of a centimeter? Did I do that right? No, I didn't. 3 thousandths of a millimeter. No, 3 thousandths of a centimeter, yeah. So that's kind of crazy. It's been doing pretty good. We just had a good result going on. So this is our lake. These are called piezometers. They're just little things that show what's known as the head in terms of hydrology, and it's just water level, but it's water level at different points. So this one is at there's a little gap here, then there's a screen, like we call it a diffusion plate. It's a piece of plexiglass that has a bunch of holes in it, and a screen over it so nothing gets through. And there's a layer of sand about that thick, and then there's the water level. So these different piezometers show what the water pressure is, essentially the head level at different points. So there's one at the bottom where there's a layer of water, one just above the plate at the start of the sand, and one about halfway into the sand. So we can monitor where these levels are at. You'll notice that they're pretty much the same. They're slightly different just because there's a little bit of head loss due to friction with the sand and the plate. Right now we have it configured. We can configure it a couple different ways, but right now we have it configured so that there is going to be water seeping in through the bottom of our lake, and it's considered positive seepage because seepage is in the positive X or Y direction. So right now it's configured to do that. We have another bucket here. There's the guy who's helping me, Daniel, he rigged up this really nice pump system so that there's another water sensor here called an E-tape, and it's a little less accurate than the magnetostrictive, but it still does its job pretty well. So every time that the water level drops below a certain point, I think it's set to 106, it's just kind of an arbitrary value, but every time it does that, it pumps more water in. There's a pump down there from this other bucket, and it keeps this at a constant head, a constant level. That's really important because we have to use non-aerated air, and so we have to set water out overnight so that all the air can come out of solution from there. It can mess up it messes up, it like sticks to stuff when it moves through sand, so we want to mirror the natural conditions. Otherwise we could have just, I don't know, hooked it up to a faucet, but we want it to be non-aerated, so we have to have this kind of system. But it works pretty well. As soon as this water level drops, that pump kicks in and pumps more water in. So this never, it just hit when I moved it and the pump went for a little bit. Like if I were to wiggle it, the pump starts kicking in, and he did it a very specific way so that I don't know, it's gentle. It doesn't just all force it, and it kind of powers and cycles. So that's kind of neat. So right now, water, this is at a higher elevation than this, so water always flows downhill. It flows through this pipe, this tube, into the bottom here. It's locked off right now because I'm not doing anything. And it comes up, and then the water level in here is controlled by this port right here. Obviously, if there's a hole in a bucket, it's going to come out of that hole, so it keeps the water level at a what's referred to as a steady state. Your inflow is going to equal your outflow. There's no change in volume here because you're able to collect it out through this tube. And we can get flow rates from that way, which is really useful. Yeah, that's basically what I'm doing right now. They also have this little thing called a Darcy Tube, a Darcy column. It's used to, that's what this yellow with these standpipes are. It's a way to measure a property of sediment known as hydraulic conductivity. It's basically just the property that lets, it is a measurement of how how well a sediment is able to let water flow through it. So we were doing some experiments with the sand that we have in this bucket, just playground sand, to figure out. We, in theory, should be able to figure out what the hydraulic conductivity is based on this one guy's method that we're testing, but we needed to compare it to a known value. So that's what the Darcy Tube is for, to get that known value. We have a couple of them actually. This one's a bit of a coarser sand, and then I'm about to make another one, this little small one, based on some samples that we collected from the field. This one, I'm setting it out to dry. I'm going to pack it soon into the Darcy column, but it has to be dry sand. So this is the cleanest sand that we collected, and I'm just drying it out, trying to get it out. We don't want it to have any cohesion to the sides because we don't want any gaps or air pockets in our sand. These are the other two samples that we collected from the field. That one was like right by this lake, so it's got a lot of organic material, really dirty, really, yeah, just organic rich. And this one was a little bit further back, still had a little bit of organic, still kind of black. But we just used it's all about the same sand. It's all beach sand essentially. They're old sand dunes is the area. It's an area known as the Munson Sand Hills. So it's kind of neat as to what we're doing. This is where Daniel's working. He's trying to got a solar panel that we're going to hook up to our device. This is the first copy of what our device is looking at. There's the tube, obviously. There's a little thing known as amplification factor. So because this is a lot smaller of a diameter than this, it should fill up a lot faster than we'd see a change in there. So that's why that's there. We have an E-tape hooked in there. That should be substitutable with the magnetostrictive unit if we desire to do so. And then there's a servo motor right here which turns this rod, and it opens up a valve in here. So when we want to measure the lake level, we can open this up, and then the head of the lake level will flow into here, and then we'll get the lake level. We'll be able to measure it with the magnetostrictive or the E-tape, the water level. Then when we close that off, we don't have any input from the lake. We just have the input from this tube, which was stuck in the ground, and we can measure groundwater levels rather, and seepage rates, and using the method that we're looking at right now. So all this stuff is a lot of 3D printed. We have a 3D printer here, and then FSU has something known as the Innovation Hub, which Daniel is very well versed in and has been printing a lot of stuff, like that cap up there, that solar panel mount. That's pretty new. I just noticed that today. A lot of the that E-tape housing, not the housing, that's PVC, but the top part there is also 3D printed. A lot of stuff is 3D printed, so that was kind of cool to kind of get to learn how that all works. And did some runs today, and we're looking for this Q value, and comparing it to a direct measurement versus using the seepage meter prototype. And for the first time, I got it on the same order of magnitude and the pretty, if it's not going to focus on this computer screen, but same order of magnitude and then pretty similar values, 9 to the negative 4 versus 8.6 to the negative 4. So pretty happy with that. Everything else, this is only one of my runs today. Earlier run, it was that's the wrong one. Order of magnitude off, which is a little disappointing. Wait, is that 1, 2, 3, 4? Oh, no. Sorry, these are different measurements. But 4 to the negative 4, 5 to the negative 4 versus 1 to the negative 4. It's the same order of magnitude, but this one is about 2 times higher, so that's not too great versus 0.8, so that's a lot better. So I'm feeling a lot better about that. We'll probably do some more experimenting tomorrow with this. There's also another setup where you can have, this is where we have water coming in through the bottom. There's also, you can have water from the lake draining into the groundwater. And this method, in the guy's paper, he was saying that it's not very well measured. And I did that test 2 weeks ago, and also found that it wasn't the easiest thing to measure. So hopefully we'll either figure out a way to measure that or refine it. But this is really, really nice because it's a tangible result of what we're looking for the first time. So that's exciting. Yeah, we'll probably move up to that using this prototype, this, like, I don't know, Mark II, I guess you could call it, version. Soon. I don't know if we're going to need a bigger bucket because that clear pipe should be partially submerged. So I don't know. We'll see. We'll figure it out. For right now, doing all right. And then also USA jobs because I'm always looking for a job. But yeah, got that. Got my notebook. Got my textbooks. And it's all coming along. Plus, we have the new building. It's starting to come along. It was raining today, but they started installing these like slats on the windows because this is the southern wall is just completely glass and it's going to get pretty hot. So I'm assuming that's what those kind of red slatted, I don't know what you'd call them, are for, just to help minimize that. But I think most everyone has gone home. There's a couple guys still here. It's about 3 p.m. Is it? Yeah, it's about 3:30. So yeah, that's what's been going on. The building's coming together. We're supposed to move in around Christmas. Nobody's going to want to move in around Christmas because they're going to want to go on vacation. So we'll find out whether I have to stay and move everything in this room across the street or not. But yeah, that's where I'm at right now. Hope you're doing well, and yeah, go Noles, I guess. I'll talk to you later. Bye. Okay, actually one more thing. I decided to figure out the hydraulic conductivity between the two runs, and they're on the same order of magnitude from the Darcy Tube versus the seepage meter. 1.8 to 8.6 times 10 to the negative 3 versus 5.8 times 10 to the negative 3. So they're close-ish. Probably not close enough for what we want, but who knows? Maybe it'll get better. Not too bad of a result. So yeah, actually, bye this time.